So I'll first give a formal definition. And one thing I should note is that context-free grammars are not only used in linguistics, they're also of central importance in computer science, both in theoretical computer science and also in programming languages where they play a very, very important role. Okay, so a context-free grammar has the following components. So a context-free grammar G is a four-tuple consisting of n, sigma, r, and s, where we have the following elements of this tuple. So n is going to be a finite set of what we call non-terminal symbols. Sigma is going to be a finite set of what are called terminal symbols. R is a set of rules. Come back to this in a second. And finally, S is some member of N, which is referred to as a distinguished or start symbol in the grammar. So each of these rules takes the following form. We have something on the left-hand side of the rule, X. X has to be a non-terminal. And then on the right-hand side of the rule, we have a sequence of items, y1 through yn, where each of these y's can either be a non-terminal n, or it can be an element of sigma. Notice that n could be 0, so actually this right-hand side of the rule could just be what we often write as epsilon, which is the empty sequence of length 0. So that's a very abstract definition. Let me give you a concrete example. So here is an extremely simple grammar for English, but it is useful in illustrating the definition that I just showed you. So I have the four elements of the context-free grammar here, n, s, sigma, and r. So n in this case, as I said, is a finite set of what are called non-terminals. So we have symbols like s, np, vp that you've seen appearing in those parse trees I showed you earlier. And notice we also have parts of speech, things like dt, vi, vt, nn, in. These are actually going to be parts of speech in the grammar. The distinguished start symbol is simply going to be s. Okay. And then finally, we have a set of words in the language. So sigma might consist of the following set of words. So we have very small vocabulary here. Moristic grammar would have a much, much larger vocabulary. And finally, we have a set of rules, okay? So here are the rules in this particular example grammar, and as I said, on the left-hand side of the rule, I always see a non-terminal, for example, S, VP, or NP, or PP, and so on. And on the right-hand side of each rule, I see a sequence of 0 or more symbols, where each symbol could be any element of N or sigma. So in particular, I have S goes to NP, VP here. If VP goes to VI, VP goes to VTNP, and so on and so on. Over here I have rules where actually the left-hand side is a single symbol, for example VI, and the right-hand side is a word, for example sleeps. So this is one simple example grammar. Later in the class we'll talk a lot more about what these different symbols mean, but just briefly, S basically stands for a sentence, VP is an abbreviation for a verb phrase, NP is a noun phrase, PP is a prepositional phrase, and so on and so on. So that's a formal definition of context-free grammars, and also an example of a particular context-free grammar. The next crucial concept is going to be the idea of a derivation, or more specifically what's called a leftmost derivation. So a derivation is a sequence of strings, S1 through Sn, where this sequence of strings has the following property. So S1 has to be equal to S, this distinguished start symbol in the grammar. Sn has to be made up of elements of sigma alone. So sigma star is just the set of all possible strings, which can be derived from sigma. So if I have sigma is the dog A, then sigma star includes strings like just the empty string epsilon, A dog there, two-word strings like a dog, the dog, and so on. Basically, any string you can form through a finite sequence of these words in sigma where we also include the empty string sigma, epsilon. Okay, so Sn has got to be a sentence, for example, the man sleeps, only elements of sigma. And then each intermediate Si, for I equals 2 to n, is derived from Si minus 1 by picking the leftmost non-terminal x in Si minus 1 and replacing it by some beta, where x goes to beta is a rule in R. So here's an example of a derivation, and actually I'll go over this example in much more detail on the next slide. So we start off with S, that's the first string. The next string in this derivation is NPVP, and that's because I've taken S and replaced it by NPVP. And then I take this NP and replace it by DN, and so on and so on. Let me actually go to an example where I'll illustrate this a little bit more carefully. Okay, so we always start in a derivation with this distinguished start symbol, for example S. And then at each step we're going to choose some rule under the grammar. So we might, for example, choose S goes to NPVP. And in this case we replace S with the right-hand side of this rule, the NP goes to VP. So the critical idea in a derivation is that at each point we take the leftmost non-terminal in the current string and we find some rule where that non-terminal rewrites as a sequence of non-terminals and we simply replace it. So the next non-terminal we're going to modify is NP. So we pick some rule from the grammar, for example NP goes to determinant N, replace NP with determinant N, and now we have the sequence determinant N VP. Again, I pick the leftmost element, dt in this case. I pick some rule, in this case dt goes to there, and now I have the N VP. And we can keep going like this. And finally, we end up with a sequence of words. Okay, so a complete derivation always ends up with a string where every word in that string is a word in the language, i.e. every element in this string is a member of sigma. Okay, so the context-free grammar will define a set of valid derivations where any derivation is valid if it starts with S, ends with some sequence of words, and goes through this process where at every point we replace the leftmost non-terminal using some rule in the context-free grammar. It's very useful to represent these derivations as parse trees. So this parse tree, which I've shown you here, is nothing more than a representation of the derivation. So we have S at the very root of the tree. Notice we've chosen S goes to NPVP as the first rule, and that's reflected with the fact we have S dominating NP followed by VP. Similarly, we have NP dominating determinant noun because that was the next rule we showed here. And so you can go through each of these rules used and see that it corresponds to some subfragment within this tree. Okay, so given a context-free grammar, we have a set of valid derivations under the grammar. And this set can be infinite. In fact, in almost all interesting cases, it's going to be an infinite set of possible derivations. So a couple more definitions, or one more definition. So we say a string S, so a sentence, so this could, for example, be the dog laughs. We say a string S is in the language defined by the CFG if there is at least one derivation that yields S. Okay, so a CFG defines a language. A language is a set of strings, and a string is in the language if there's at least one parse tree for the string. Critically, a very interesting property is that some strings in the language may actually have more than one possible derivation. And this leads directly to the problem of ambiguity. Let me give you an example of this. So here's a very simple sentence. He drove down the street in the car. And here I have one possible parse tree for this particular sentence. But under most grammars for English, there will also be a second possible parse tree, which I've shown you here. So let's go back and forth between these two. So in this particular parse tree, this prepositional phrase is seen lower in the tree. And in particular, I have a rule NP goes to NP prepositional phrase at this low level in the tree. Whereas if I go back to the previous parse tree, you'll see again we have this prepositional phrase in the car. But it's a little higher in the tree. In particular, we have a rule VP goes to VP prepositional phrase. So basically, there is some ambiguity about whether this prepositional phrase is seen high in the tree, attaching to this VP, or if it's seen lower in the tree, attaching to the noun phrase down here. And that actually corresponds to two different possible interpretations of this sentence. So under this parse tree, in the car is modifying this entire verb phrase down the street. And this basically corresponds to by far the most likely interpretation, which is that I'm doing the driving in the car. Let's look at the second parse tree, though. In this case, we have in the car modifying street. And so there is a possible, although highly implausible interpretation, where the street that I'm driving down is actually located in the car. So I have a street in the car. You could imagine some crazy world where that could happen. And that's what this attachment corresponds to. This is where the prepositional phrase in the car modifies street, and so we have a street in the car. So, just to recap, critically, with an underlying context-free grammar, you may find that there are multiple derivations for a particular sentence. And those multiple derivations very often correspond to different interpretations of the underlying sentence. So let's illustrate this issue of ambiguity with the following sentence, which is a quite short and rather innocuous looking sentence. She announced a program to promote safety in trucks and vans. And to human, there's really only one plausible interpretation of the sentence. It's really not ambiguous. But as we'll see, there are actually several possible syntactic structures for this sentence, corresponding to various different interpretations, most of which are quite unlikely, but all of which are nevertheless syntactically well formed. So let me give you an example of just a couple. So she's announcing a program to promote safety in trucks and vans. So you have safety first in trucks and secondly in vans. These two things are coordinated together. We have trucks and vans together. But under another interpretation, she could be announcing a program to promote, firstly, safety in trucks, and secondly, vans. So I am announcing a program to promote safety in trucks and also vans. Okay, so much less plausible, but nevertheless a potential interpretation of this sentence. Here's another example I'll give you. Okay, so on another interpretation, she could be announcing a program to promote safety where the entire program is located in trucks and vans. That corresponds to an interpretation where this preposition in is modifying the program. So the program is actually located in trucks and vans. Again, a crazy interpretation, but a valid one for this particular sentence. So you can play around with this, and you can actually find many more. I think I found 14 different possible syntactic structures for this particular input example. That's a surprising amount. And what you can basically see here is these different points of ambiguity multiply out to give different interpretations. So for example, I could coordinate trucks and vans, which is correct, but I could coordinate vans and safety, which gives you another interpretation. This preposition could be modifying safety, or it could be modifying program. Actually, it could also be modifying promote, or even announced. You're going to get many different interpretations under these different places that this prepositional phrase can modify the preceding words. Okay, so firstly, let's talk about some very basic parts of speech. These parts of speech conventions are taken from something called the Brown corpus. This is a corpus from the early 1960s, where actually a group of researchers took a pretty diverse set of sentences from a wide variety of genres in English and annotated their parts of speech. So this is quite likely the first part of speech tagging corpus. And the tagging conventions have been used in many other corpora since that. So if we look at nouns, we actually subdivide these nouns into a few different subtypes. So we have singular nouns, we use the tag NN for a singular noun. Plural nouns, we use the tag NNS for a plural noun. These are things like telescopes, houses, or buildings. Singular nouns are things like man, dog, or park. And finally, proper nouns, we use NNP. This is the part of speech tag for a proper noun. These are names, things like Smith, Gates, and IBM, almost always capitalized words in English. Moving on, a second very important part of speech is DT, which stands for determiner. So determiners are words like the, or a, or some, or every. Determiners usually come before nouns, and so I can have strings like the man, or a man, or some men, where I see a determiner before a noun. And then finally we have adjectives. So JJ is used to refer to an adjective. An adjective could be a word like red, green, or large, or idealistic. And adjectives often come between determiners and nouns. So I can have strings like the red telescope would be one example where I have a determiner, then an adjective, then a noun. Okay, so I'm next going to start to build up a simple grammar for what are called noun phrases. And a noun phrase has this category NP. And let me show you how these rules work to give us several different noun phrases in this language. Okay, so the rules over here have parts of speech rewriting as various words. For example, this rule says that the part of speech NN, remember that's a singular noun, can be a box, or we can have NN rewriting as car, or mechanic, or pigeon. We have two words for determiners. DT can rewrite as the, or a. And then I have a few adjectives over here, fast, metal, idealistic, clay, and we have JJ, this adjective symbol, rewriting as each of those words. Okay, so let's see how we can construct phrases of type NP. And let's start with a very simple one. So I can use this rule here to say that a noun phrase consists of a determiner followed by a category called an N-bar. Refer to this as N-bar. It's an N with a bar above it. And we'll see soon what role this plays. A determiner can rewrite, for example, as the. An N-bar can rewrite in various ways, and we'll come to these other rules later, but for now let's just use this first simplest rule, where an N-bar rewrites as a singular noun, and then finally the NN, the singular noun, can rewrite, for example, as car. Okay, so that's a first very simple example of a noun phrase corresponding to the car, and it has this kind of internal structure. So a noun phrase will generally consist of some main noun with some material before it, some words often called pre-modifiers, which come before that word. In this case, we have one modifier, which is the determiner there. And under this grammar I've shown you here, a noun phrase is always composed of a determiner followed by a category called an N-bar. Okay, so let's try a second example. So again, I have NP goes to N-bar, sorry, determiner N-bar. And now I'm going to make use of this rule, which says an N-bar can be formed by an adjective followed by an N-bar. So I use this rule. And similarly, I can use n bar goes to n, and then I can say jj goes to fast, and nn goes to car. Okay, so what do I have here? I have a structure for the noun phrase, the fast car. And notice that critically I've used this rule which says that I can create an n bar by an adjective followed by another n bar. Okay, we can go a step further, and it's important, we'll see how this rule, n bar goes to jj, n bar, is recursive in that it can be repeatedly applied. So let's give a third structure. So again, I have this rule at the top. But now I'm going to apply this adjective rule twice. And so I can have things like the fast red car. Okay, and you can see how you could repeatedly apply this adjective rule, so you can get multiple adjectives before a noun which are all modifiers to that noun. Okay, so that's an example of how we can use this rule here. Let's move on a little bit, and let's now look at how this rule can be applied. So I have a rule saying an n bar can be formed by a singular noun followed by an n bar. So let's give some examples. So again, I can have np goes to determiner n bar at the top of this. We have there. And now I'm going to use n bar goes to nn n bar. So that's where I've used this rule here. And here's an example of how this rule might be used if I have a car factory. This is a factory that makes cars. You notice that I have car acting as a pre-modifier to factory. So it's almost in the same position as an adjective, but this is definitely a noun. But it's a rather similar construction to the one we just saw with adjectives. Okay. Moving on, let's finally look at this rule here, which says that an n bar can actually be formed by an n bar followed by another n bar. Let me give you one example of how this rule can be applied. So again, at the top we always have np goes to determiner n bar. And now I'm going to make use of this rule. So maybe again have factory down here. Okay. But now I'm going to make use of this rule. So let me write the structure and then we can go over it. So what I have here is a string that says the fast car factory. Okay, so this is a factory that makes fast cars. And now I have this entire n bar fast car as a pre-modifier to factory. So I've replaced car here with this entire pre-modifier fast car. Okay, and that itself has the category of n bar. So you can see how this n bar category is being used as an intermediate category within these noun phrases. We always see n bar following a determiner, and in addition, n bar can be used further down within these trees.
So the idea of dependency syntax is you connect up the words of a sentence by putting arrows between them that show relationships of being modifiers or arguments of other words. So here in this example, we've got the head of the whole sentence submitted, and it's got its dependents. So it's got bills submitted by somebody, and then also the auxiliary verb were. Now, not necessarily, but quite commonly, the arrows are typed by the name of some grammatical relation. And so we can see that here, where we've got the subject of a passive, the verbal auxiliary, and the prepositional relationship. The other things that you should know about is just a bit of the terminology. So firstly, when we have an arrow, we always have the thing that is the head or the governor here submitted, and the thing that is the dependent, modifier, inferior, various words are used, as you can see over here, bills. So that they're the two ends, the governor and the governed thing of a dependency. Now, beyond that, there's actually some inconsistency about how things are done. So in these slides and in the original dependency grammar work of Tesnier, the arrows run from the governor to the dependent. But you can absolutely also find other work that points the arrows the other way. And actually, if like here, you're using height in the tree to show what's dependent of what, you actually don't need to have any arrows at all. You could just draw these as lines without any arrowhead on them. Okay, so as in this example, normally what you find is that dependencies form a tree. So that there's a root node, and then from there, everything heads down with words having a single head and in an acyclic manner. I should mention also that it's actually quite common to add sort of one pseudo node at the top, often called root or wall, which points at the head of the sentence. That actually makes things a lot cleaner, both in terms of the parsing algorithms, but also in terms of things like evaluation and representation, because then you get the property that every word of the sentence, including the root, is the dependent of one thing. And so you can think of it as doing an assignment process of working out what is the governor of each word of the sentence. How does dependency grammar relate to the kind of phrase structure grammar that we've concentrated on so far? Well, the central innovation is really that dependency grammar is built around the notion of having heads and dependents, whereas the basic case of a context-free grammar, there's no notion of a head whatsoever. But actually things have moved on from there. If you look at modern linguistic theory, that means things like X-bar grammar to linguists, or our modern statistical parsers, whether the Charniak-Collins or Stanford parser, all of them have a notion of head and use it extensively. So for example, in all these parsers, there's a notion of head rules where it'll identify some category as the head of a larger category. And as soon as you have head rules of the kind that we discussed before, well then you can straightforwardly get the dependencies out of a phrase structure representation. So basically you kind of have a spine of head chains, and then everywhere you have something coming off that, that's a dependent. So we have a dependency from walk to Sue, and a dependency from walked into. This is another head chain, and then we've got another dependency from into store, head chain, and dependency store the. So we have the basis for a dependency representation inside a phrase structure tree if and only if we have heads represented. What about if we go in the opposite direction? If you try and go from dependencies to phrase structure, you can reconstruct a phrase structure tree by taking the closure of the dependencies of a word and saying that those represent a constituent. But it slightly changes the representation from what we normally see in phrase structure trees. In particular, in a situation like this, you can't have a VP node because actually both Sue and into are dependents of walked, and therefore all three of those must have a flat phrase structure representation where you have the head and its two dependents, Sue and into. How do people go about doing dependency parsing? A whole variety of methods have been used for dependency parsing. One method to do it is with a dynamic programming algorithm like the CKY algorithm that we saw for phrase structure parsing. Now, if you do this naively by adding in heads, you end up with something similar to the lexicalized probabilistic context-free grammars we saw earlier and end up with an O big N to the fifth algorithm. But there's a clever reformulation of what the parse items are due to Jason Eisner 1996, which makes the complexity of doing dependency parsing also n cubed, which is kind of what you'd hope it to be, just thinking about the nature of the operation. But there are a whole bunch of other methods. So people have directly used graph algorithms to do dependency parsing. So one idea from the algorithms literature is that you can construct a maximum spanning tree for a sentence, because since you want all words connected together to be the dependent of something, that means you have to build a tree that spans all the words in the sentence. And that's the idea that's used in the well-known MST parser. There are other ideas of constraint satisfaction where you start off with a dense set of edges between all words and then eliminate ones that don't satisfy hard constraints. But a final trend in dependency parsing, and actually what we're going to focus on here, is a way of doing dependency parsing where you head left to right through the sentence and make greedy decisions based on machine learning classifiers as to which words to connect to other words as dependents. And so the most well-known example of this framework is MALT-Parser. And I'm going to concentrate on this just partly because it's very different to what we did for our approach to phrase structure parsing we looked at in depth, but also because it's been shown that this kind of method of doing dependency parsing actually works extremely well. It can work accurately and exceedingly quickly. So it's just a good thing to know about as a different point in the space. No matter how we do dependency parsing, we need some sources of information to let us choose between possible analyses and which words to take as dependents of other words. So here's a list of the main sources of information people use. So the most obvious source of information is bilexical dependencies. So if we have something like a dependency between issues and the, well, we can look at the word that's the head and look at the word that's a dependent and say, is that likely? That's similar to the bilexical dependencies of our earlier lexicalized PCFGs. But we don't want to use that as our only source of information, partly because lexical information is so sparse. And there are several other good sources of information. So let's just go through those. So one is the distance between the head and the dependent. And if you look at this picture, what you'll see is that most dependencies are short. They're with nearby words. There are a couple of exceptions. So this dependency here is a pretty long one, but most of them are pretty short. Other sources of information are what is the intervening material. So in general, dependencies don't cross over verbs, and commonly they don't cross over punctuation. Some exceptions, commas are quite often crossed over. So looking at the words in between can give information about whether a dependency is likely or not. A final source of information is looking at the valency of heads, and that's saying for a particular word, what kind of dependence does it typically take? So a word like the typically takes no dependence on the left and no dependence on the right, as in this case here. On the other hand, if you have a word that is, say, a noun, it will take dependence like adjectives and articles on the left, but it won't take those kind of dependence on the right. But it can take other kinds of words as dependence on the right. For example, take prepositional phrase modifiers or relative clauses as dependence on the right. So you can develop a quite rich typology of what kind of dependence words take.